Thank you so much for coming. I really appreciate your time coming today to hear me talk about computer science stuff, theory. Exciting stuff for 9 a.m., I think, on a conference. I hope your heads aren't too full of the information here this week. This is my favorite conference, by the way. I love coming here, and I hope you guys come back every single year. It's awesome. Okay, so today I'm going to talk about, again, computer science and theory and stuff, and I'm going to try and not make it boring. If I do my job right, I will share with you some of the theory and some of the interesting concepts that I actually use during my day job, which is true. And I should point out that I do not have a computer science degree. And actually, this slide is reminding me, I'm supposed to say this like a cowboy, because evidently if British people do American accents, they always sound like a cowboy. So I'm going to say sometimes you get a degree. Well, yeah, sometimes the degree gets you. So I don't have a computer science degree. I have a geology degree. So I had to learn this stuff for myself. And the interesting thing about that is I was able to move along in my career just fine without a degree. I didn't need it, and I'm not actually here to debate whether you need one. I'm going to sidestep that whole thing. What I do think is that concepts that you learn when you get a degree are actually quite important. So a few years ago, I decided to change all of this and learn these things for myself. Went online, and I watched some programming stuff from MIT, from Stanford, and from other places. And I just kind of dug in. I looked at the curriculum that is normally involved with a computer science degree, and I said, well, all right, I'm going to give it a shot and see what happens. And I had a good time doing it, and so I'm going to share some of that with you today. So speaking of, what is my day job? What do? I work at Microsoft right now. I used to work there back in 2008. My friends had a good laugh when I went back. They thought it was hysterical that I'm back behind the Azure curtain, as they said. So I'm actually, what I do is I work in developer relations, and I am not an evangelist, despite the fact that I'm standing up here talking about Azure right now. I swear, though, I'm not. I don't go to conferences. What I do is I break stuff. I was hired to build things and break Azure. That's what my boss said to me. We want you to come in here and break Azure. I'm like, are you serious? Because that sounds like a pretty good job. So that's what I do. I try and stress out the Azure services. So I could just go the normal route and build normal web applications or whatever applications, but I have to get in there and try and figure out how to use these services the way that y'all might. And I've actually managed to break Azure and indeed see behind the curtain there. It's actually been a lot of fun. Okay, so what exactly are we talking about today? I'm going to dip into data structures. I'm going to talk about big O. Please don't leave. Just hang tight. I'm going to try not to make it boring. Nasty big O. And if you don't know what big O is, it's just a way to talk about efficiency of an algorithm, which I'll explain later on. I'm going to talk about complex problems, and then super nasty complex problems, a pinch of NP. Now, I was talking to some friends about this talk and telling them what I was going to go over, and they said, they're going to think you're just up there saying, look what I know, strutting my stuff, and I don't know, trying to peacock, I think as someone said. I hope that I don't come off that way, because this stuff is really fun to me. Now, I know there's also some of you out there who are going to say, you know, you're up there talking about CS degree, that's really boring, and a lot of this stuff is really obvious. What I'm hoping we can do is go somewhere in the middle and just sort of geek out, and for an hour or so, just sit here and go over these concepts and have some fun. That's my goal. I'm not up here to try and show you all how exciting and smart I am. Okay, so the first thing I wanted to go over is data structures. We learned about these, or maybe we just started using them and figured it out as we went, like I did. Arrays, linked lists, dictionaries, hashes, stacks, queues, things like that. You might not have to think about these things every single day, especially if you use something like Entity Framework, Link, if you use Active Record, or these platforms. They just handle a lot of this stuff for you. However, recently I was building an application with Elixir. The slide I showed you before was this thing called Tailwind. It's the successor to Northwind. It's kind of the new demo stuff at Microsoft. So I'm building out all these e-commerce storefronts. I'll come back sometime and tell you what I'm doing, but basically trying to build these implementations so I can put them on Azure. So one of the things I'm doing is I'm using Redis. I'm trying to build this thing called a headless e-commerce thing, or headless e-commerce store, which is basically just an API, no front end. And I want to make it as screamingly fast and scalable as I can. So I'm using Elixir in a cluster, and I'm putting everything in Redis. And if you've ever used Redis in a non-trivial way, you have to understand the way that Redis data structures work. That's how Redis stores data. Now, as developers, we either use a document database, maybe a key value store, a relational database. You don't really get a choice. You store something in a table, you store something in a document, then in a collection. In Redis, you actually have to decide what structure you want to save it in. And so then, as I'm building this out, I'm like, well, geez, what are these things? I'm kind of glad I studied this stuff because I feel like I need to know it. Because I'm trying to build out a shopping cart. I'm taking a really trivial example here. But I sat there and I was thinking to myself, how do I build a shopping cart with bare metal Redis? What data structure do I use? So I know I could Google it. I know I could just go and Google it, see what everybody else says, hit Stack Overflow, get scared, freaked out, yelled at, and then figure out that maybe, I should just use what they say and don't come back here. Just kidding. Hi, Jeff Atwood. So I decided to dive in and figure out what to do with a shopping cart. And so I wrote down the considerations, which are pretty basic. I need quick access to the cart. I need quick access to the items in the cart. I need to enumerate those items, blah, blah, blah. It's pretty simple, straightforward stuff. We all understand this. So with Redis, the way you set this kind of thing up is you come up with a key for the data structure you're going to be storing. This is how you write that key. It's some general term, some other term, and then a unique term, separated by a colon. So I thought, well, okay, I have a bunch of items that I want to store into a cart, so I'll just use a list. Sounds right to me. And so here's the definition for a list. Simple enough, collections of string elements, and they are basically linked lists. And that one stuck me, because I was just reading about linked lists. And so in my head, I'm like, oh, I just read about this. How exciting. I know what a linked list is. But then I'm looking at the methods that you can see down below, lpop, lpush. These are the methods that you use in Redis to work with data in this data structure. So pop and push, and as working with programming as we do, we know that pop and push usually is something with an array or something. Well, the literal data structure that has pop and push on it is a stack. So the last in, first out, you push an item onto the stack and pop it off the top. That's the way stack works. And I'm thinking, well, that's not, it's a derivation of a linked list, but how am I supposed to do this? I'm getting confused. And then I thought, what's L and R? And that's left and right. So you can left push an item onto a list and right pop it. Put it in one end, pull it out the other, that's a queue. I'm like, okay, I think I'm starting to see this now, that what a list is, it's a stack or a queue depending on how you use it. Okay, well, is that right for a shopping cart? And I'm thinking, I don't think so. I think there might be something better, but let's test run it. And just to geek out and nerd out a little bit, I opened up Redis. This is the Redis CLI. I did the operation, lpush. As you can see, there's my cart, sales, cart, Rob. And then I pushed in skew1, just a string value for now, just to test this out. And I was able to push in 2 items. Unfortunately, to pull the items back out, I had to do lrange, which means give me the range of items, right? And I was able to do it using the explicit 0 and 1, the first item, second item, or 0, 100. Redis didn't care. It gave me everything back. This didn't quite work for me, because I need to be able to get to each item individually. So I thought, well, let's move on and try a set, because a set is like a list, and the definition is right there, but it's a bunch of unique string values inside of Redis. So I tried to do set add, and let's see if we can work with the items in my data structure a little bit easier. I want to be able to get at the items. And this didn't really work. It sort of worked. I was able to do S members, which gives everything back, but I wasn't able to get at each individual member. So here's a more realistic view of what I was trying to do with this set. I was trying to store some JSON, right? So that each item in my cart is just going to be a JSON thing. And then I thought, well, I could do this. If I need to get at an individual item, I'll just pull all the items out, loop over it, and then pull it out by skew, and I'll be okay. But then I was like, that's just not terribly performant. And I wanted to make sure that everything was fast. And if I have a loop in there, that's not the fastest it can be. And I think Redis can do better. Now, I know some of you out there who might have used Redis before probably sitting there going, dude, just use a hash. Get to it already. So this is the thing that most people use when they use Redis. If you use a tool that helps you use Redis, some kind of ORM or whatever, they typically will help or will store values in a hash. A hash is just a key value structure that you store data with. It's like in JSON, it's just a big fat giant hash. So I was like, okay, I could do this because what this allows me to do is to have a little property in there, or a subkey. So now I can store items in there, and I can give that unique item, or an item a unique key, which is skew1, skew2, followed by a dump of JSON. To verify this, I used some real data. This is some test data that I was using, but I wanted to see what it would look like if I pumped in some JSON, and there you can see I can now reference things directly. I can also loop over all the items in the cart with hgetAll, get all the keys, all the skews. I'm stoked. Let's use a hash. Well, that's only half the story. The data structures that you use also dictate the code that you're going to be writing. Now, again, normally you don't have to worry about this if you're using some kind of framework like .NET or Ruby on Rails or whatever you're into. You don't have to worry about this stuff, but when you're trying to get really deep in under the covers and tweak things, using Redis, for instance, you have to understand the other half of the story, which is where we talk about big O and the influence of your data structures on your performance. And at this point, people roll their eyes, and I've talked to other speakers here, and they're like, what are you talking about, big O? Like, you're jealous, you know. And there's a lot of people who just don't really like to hear this stuff because it reminds them of interviews. For me, I kind of found this a fun mental challenge and a neat little puzzle. So what is big O? What does it mean? It is a way to mathematically describe the performance of your code. That's it. So in this operation, I'm accessing my hash, I'm accessing an item in the cart. I'm having to do one call to get that item. And when you're using Redis, you have to know your big O because the structures determine the efficiency of the code you're going to write, as I mentioned. So in this case, what I wanted to do is I wanted to make that access on the order of one operation only. I don't want to have to loop over something because that's more. I just wanted to have access of one operation. So instead of using all those words, I can just say order 1. And that's what big O does for you. It just kind of makes everything succinct. And when you say, oh, this is order 1, then the idea is I just have to do one thing to get the thing I want. In this case, if I'm using a set and I have to enumerate over everything, that is not one operation. That's a lot of operations. Well, how many? Well, we don't know. We don't know how many items are going to be in the cart, so we just say n, order n. So when a loop is involved, order n. In fact, that's one of my little tricks when I'm working with big O. How many loops are we talking about? If there's a loop, then it's order n. If there's no loop, it's order 1. No loop here, order 1. And then I can look at this and think in my head, well, to work with this, it's order n. Woohoo, big deal. What if I had a situation where I'm using a set and I accidentally dumped in a different quantity? Well, Redis is going to see this string as a different string from the one that was there before. And it doesn't know that you're giving it JSON. It just knows that the two strings are different. And so what I end up with is a duplication. And so this is also one of those interview questions. How do you dedupe an array? And if you guys are thinking about it right now in your head, you might think, well, you got to loop over it and then loop over it again. And the same process goes here. I'd have to loop over the cart, and then I'd have to loop over the cart again for the item that I'm currently iterating over to see if it's already in the cart. And if it is, then I can go do my thing. Well, if you do a nested loop like that, you're looping n times, and then you got to loop n times again. So it's n times n, which is order n squared. Those three things, I swear, are the only big O considerations you probably are going to have to ever deal with. In fact, when you're talking to your boss, you're talking to somebody, you're doing a code review, it's pretty common, at least in my world, it's pretty common for somebody to look and say, you got an n squared over here, can we get it down to order n? And that right there is a really fun challenge. How do you get away from a nested loop? We'll talk about that more later on. And I know what you're thinking. I'm really glad I'm not using Redis. And a lot of people have had that feedback when I tell them what I'm talking about today. They're like, why do you even bother? Just use Entity Framework or use whatever. It takes care of all this stuff for you. And of course, me, challenge accepted. Let's see if that's true, because that's just like your ORM, man. I don't think that's really going to do the thing that you think it's going to do, because I like to know. That's the thing with me, is I don't just like to take someone's word for something, which is really annoying, and it tends to piss a lot of people off. I suppose over here you say cheese them off, is that right? I don't know, is that bad to say? Never mind. So I decided to dive in and figure out, what are we talking about here? Really, is using an ORM a better thing? So this right here is some code for Entity Framework. This is Link. I'm sure you all have seen this before if you've done Microsoft stuff. And what this is doing is a simple query. This is just doing a single lookup, select star, from my film table where the title equals something. Now, a quick review, if we take a look at that code right there, that's only doing one thing, which is good, right? That's what we want. It's order 1. So you're thinking to yourself, I'm fine. Why do I need to worry about anything else? I'm at order 1. That's true, but let's talk about what your database is doing. How is this query affecting your database? Now, let's say we have 1,000 rows in our film table. If I ask Postgres, which I can do by using explain, analyze, and passing it the query that I'm writing, if I ask Postgres what's happening, Postgres is going to tell me, well, I have to perform a sequential scan. In SQL Server land, this is a full table scan. What that means is that the database engine has to loop over every single record and do that string comparison for the title argument. Every single record. That's order n. It has to loop over it, right? So 1,000 records, not a big deal. Database is pretty fast. 1 million records, now we're starting to slow down. 10 million records, this is a problem, and your DBA is going to be knocking on your door. And they're going to say, I need to use an index, or whatever. The DBA is probably going to do the index for you. But let's say it's your boss knocking on your door. Why is everything so slow? Why does your code suck? And then you say, well, I think I read this dude's blog and he said use an index. And so, all right, you use an index. And then your boss might say to you, all right, use an index, queries are faster. How much better are we getting with this? I don't know. You can shrug your way through that, because most people do. I did, right? I don't know, we're just faster. This guy that was on stage at NTC London said to use an index, and I don't know. Let's find out how much faster. Now, let's know exactly, because that's what Big O tells us. Math, we like math, woohoo! So this is when we get into the exciting world of database indexes. Are you guys excited? It's 9 o'clock in the morning. What else are we going to talk about? So I put butterflies and kitties up there. When you create an index, and again, this is conceptual. It's every database does something a little bit different. But conceptually speaking, this is accurate. When you create an index, what happens is the database engine grabs the data from the table and the column that you're indexing. And then it puts it into memory and it sorts it. That's it. So this is what an index might look like if you peeled back the covers of Postgres. Every time that you add or change data in the table that you're indexing, Postgres has to rebuild this index, or SQL Server. So the way that it uses this index is when you query on it, like we are here, when you query on, do a query, it'll check to see if there's an index that it can use to make the query faster. In this case, it'll see the index for the title, and it'll go in and it'll slice that index in half. And it's going to do what's called a binary search. And this is another one of those lovely algorithms that you get to study when you're going to interview for a job. But this is basically how it works. It slices the list in half, and then it looks right at the middle, and it sees an M and an N. And it says, OK, N through Z I don't need because I'm looking for a title that begins with an A. So I need all the A records. So it slices it in half, and then it slices it in half again. And so this time you'll see A through F, and then G through M, and then it looks at F through G, or it looks at F and G, and says, I don't need G through M records. I'm going to get rid of those. And it keeps on going, slicing the list all the way down until it gets from A to B. Then it goes and looks at all the A values. It keeps on slicing, blah, 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 until it finds the thing it wants. This is called a divide and conquer algorithm. It's binary search. It's one of the things that you learn when you're taking or getting a CS degree, and also when you're interviewing and panicking. So the way that this works mathematically, you can think of it this way. It's like an inverted tree, inverted binary tree. So if we start with 8 values in the top, slice that in half, we have 4 left, slice that in half, we have 2 left, and then eventually we're at 1. So put another way, mathematically, that's 2 cubed, 2 squared, 2 to the first, 2 to the 0th. So this is logarithmic. Logarithmic is, well, it's like division is to multiplication, logarithms are to exponents. That's as far as I know mathematically. And my Googling, I'm not a big math person, but it's kind of good to know this. Divide and conquer, dividing everything down until you get to the thing you want. Whoop-de-doo, who cares? Why do I care about this? Because what I can do now is open up a calculator, and I can say, what's log base 2, binary, right? Log base 2 of 1,000, because I have 1,000 records in my database. Log base 2 of 1,000 is 10. That gives us a concise way of telling our boss, or our code review person, exactly the performance that we're getting now. We are getting log n as opposed to order n. So in other words, instead of going and looping over 1,000 records, I'm only looking at 10. And we could do 1,000,000 records, and someone might have to Google that for me. I don't have it off the top of my head. But it could be like 1,000,000 to 17. Instead of doing 1,000,000 loops, we're doing only 17, which is exciting. I think that's exciting. Who's excited? You guys are excited. Come on. It's math, man. Come on, it's math. 9 a.m., everybody's enjoying math right now. OK, well, here's another little bit of trivia. This query right here is a primary key lookup. So knowing what we know now about Big O, right? We're all Big O experts at this point. What kind of operation do you think this is for your database? So film ID is the primary key. We have an integer key, right? What kind of efficiency, time complexity, Big O, are we getting from this query? Who thinks it's order 1? All right. Hey, I thought so too. Turns out it's not, believe it or not. If you ask Postgres what happens behind, or SQL Server, any database, it has to use an index to find that value. Now, it's an integer. It's an integer as opposed to a string value, so it's going to be a lot faster. That's why primary key lookups tend to be faster if you use integer keys. If you've ever been in an argument with the DBA before about, come on, man, I just want to use a GUID, and they're like, use an integer. Well, this is why, because that index scan goes way faster when you have an integer. But the interesting thing about this is that we know that an index scan is order log n. We know that that's not order 1. So what does this mean? And this is a broad statement. Somebody could come up here and throw me off the stage if you want to. This means extrapolating back that the best performing query that we can get in terms of time complexity in a database under almost any circumstances is going to be log n, which is interesting. Contrast that with Redis. And I'm not up here to try and tell you to use Redis, but I'm saying that when you understand these big O concerns, your brain starts to clink and, wow, can we squeeze out more performance if we use Redis as some sort of middle layer that holds a ton of data and we can have order one access? You can, but you run into some trouble. Let's just talk about that real fast. Because what if you wanted to find something, let's say we're storing our sales catalog, right? We want to find something by name instead of by SKU. Well, you can't do that in Redis. Redis only has one facility, which is to find something by a key, or a subkey in this case. If we wanted to do that, we'd have to pull all that data into memory and loop over it, so that's order n all the time, because we have a loop. You might be sitting there with your boss that says, you convinced me to use Redis and you're doing an order n scan, you got to fix that order n, that's not cool, man. And like, all right, and then you start thinking, how am I going to fix this? In Redis, does Redis have indexes? And this is the fun part about using Redis. Well, of course Redis does not have indexes. You get to make it yourself, which is fun. I think it's fun. You guys think it's fun? I think it's fun. It's exciting. Let's do it ourselves. So an index, well, it's just another hash, right? All you have to do is we just create another key, sales catalog, and this one we'll call name index, and the key is going to be the thing we're looking for, which is the title. And then we just add the SKU as the value. Did we get an efficiency gain here? Because we're going to have to tell our boss, right? She might say to us, you said Redis, where's my efficiency? What are you doing? This might be the code that you're going to write. So we are using the Redis library. This is JavaScript. Using the Redis library, getting a product by name, we're pulling out the SKU, and then we're going to do another operation down here, and we're pulling out the product by the SKU name. So I wouldn't blame you if you looked at this code and said, 2 operations, that's an extra database call. That's not going to be more performant. I don't care about the network stuff. I'm not talking about network stuff right now. I'm not talking about I/O. I'm talking about pure time complexity. So if I have 2 order 1 operations, does anybody know what the overall operation is? Shout it out. Go ahead. Order 1. That's right. Still order 1. This is kind of an interesting thing to know about big O notation. So if I'm looping over the same data and I do it 100 times, that's still order n. It's only when I nest it that we get into n squared. All right, so that's big O. I'm going to glance off that right now because I know people really enjoy talking about big O in the morning. Why do we care? In the real world, this is the way I kind of use big O as I'm writing these things. I have to sometimes dip below the abstractions, dip into underneath the frameworks, understand the language, understand the database, because I want performance. And someone accused me the other day, they said, it's kind of micro-optimization. Why do you think about that stuff up front? And I'm thinking, I'm not thinking of it up front, I'm just thinking of it as I'm writing the code. That to me is fun, I enjoy that. So I ask myself these questions when I'm writing code. Is that nested loop a good idea? You're going to see later on that, yes, indeed, I had to do something with a nested loop, and it was okay. Is order n the best we can do here? And that's one that you usually need to know if you're in an interview. I'm going to talk about interviews later on. Hopefully you guys don't leave. And then should I create an index? And that is a big concern. That is a big thing, because we just saw what performance gain we can get. Order n to log n, that's a big jump. And I have a little rule that I have just for myself that I don't want order n in production. And now that we've gone through big O, and I can say this to you, and you go, well, that's actually, yeah, why wouldn't you use an index? Why wouldn't you have a log n on a table as opposed to an order n? I mean, you shouldn't, at least nothing that I can reason through. So anyway, that's just a little Rob's rule. So knowing all this stuff helps me avoid embarrassment. At least I try. I seem to enjoy embarrassment. You know, it seems to be one of my things. I don't know why. So when I talk about embarrassment, I mean that you will at some point have to go through an interview. And hopefully you'll be one of those lucky few people that goes to the interview and they don't ask you really stupid questions. They don't ask you to do FizzBuzz, for instance, even though they will ask you to do FizzBuzz, and they will ask you stupid questions. It's just something that we have to do. But you also might be in a code review where someone asks you about a piece of code you wrote. You can now answer concisely instead of waving your arms and saying, well, I could now access it directly and loop. Oh, no, I'm doing order 1, man. I'm all good. And then finally, you might have some code that you do in open source. It's up on GitHub. And someone comes along and says, this is an n squared, man. I don't think this is good. Let's fix it. Oh, wow, n squared. I didn't know that was there. So let's talk about the first thing first. And you knew this is coming. Boom. Fibonacci. Thank you very much. Stay, please. Don't leave. Fibonacci. Okay, who's ever had to answer Fibonacci in an interview? Anybody? Anybody? Oh, wow, it's not very many people. If you don't know what Fibonacci is, Google it quickly. You will be asked this in an interview at some point. I think this is an awesome question. Not because you need to learn Fibonacci to get a job, because you won't be writing Fibonacci at your day job, I promise you that. But what you will need to do is you'll need to be able to spot the problems that Fibonacci brings up, because it is one heck of a crappy algorithm to drive you into a corner. What do I mean by that? A Fibonacci sequence is what you see here. It's just a sequence of numbers where the number that you're at is the sum of the previous two numbers. And I wrote a little lambda function down below there that is probably the worst possible answer you can give to Fibonacci. And this might be the lead-off question. The interviewer might pose this to you and say, do you recognize this? Yes, it's a lambda function. You can also restructure it like this if you're more comfortable reading it this way. What's wrong with this? And this is when people get put on the spot. They're like, I don't know. Why do I care? Well, to me, I look at this and I think this is kind of fun. Okay, so what is wrong with this? Let's go the extra step instead of getting upset and then saying, well, I got a fib function here and it's taking a number. And that's going to tell me what the nth Fibonacci number is in a Fibonacci sequence, right? And then down below there, I'm returning two other calls to fib. This is recursion. We can recognize this. One call spawns two more. This is a disaster right here. That is a time complexity disaster. Why, though? What is actually happening? Well, let's visualize this. If I'm calling fib 10, what's the 10th Fibonacci number? I'm starting at the top, and I've got fib 10. That's going to spawn two more calls to Fibonacci, right? So then it's going to be fib 9 and fib 8. And then those are going to spawn two calls. Those are going to spawn two calls, and so on. Does this tree look familiar to you? Yeah, this is what we just looked at. So at the very top there, we've got 2 to the 0, 2 to the 1, 2 squared, 2 cubed. Anyone want to take a guess what time complexity, what big O we're looking at here? This is exponential. 2 to the n, or n factorial. They're both kind of the same. This is literally the worst complexity you can get. We're going to talk about exponential complexity more in a bit, so I want you to remember what you're seeing here. Someone asked me, why is this so bad? Why? I don't understand why exponential complexity is so bad. They actually ran the code, and they said, well, I went to get the 20th Fibonacci number. It still came back under 0. Under 0. It would even register. It was barely even a millisecond. So if you were to run the code I just showed you and did some console log statements, this is what you'd get. It's not a big deal, right? We got all the way up to 24. We're still under 0 seconds. But then you get to 40. So the Fibonacci numbers that we're doing are all on the left side there. And you can see how many calls are made. You get to 40, we're now taking a second. You get to 48 and you turn your computer off because it's taking too long. It's just that small step that shuts everything down. That is the deal with exponential complexity that a lot of people don't quite get, because we usually deal with exponentially complex problems on a small scale, which is fine. We tend to be able to work through those. But it's only when the numbers go up that we get into trouble. Remember this, because we're going to come back to this. All right, so your interviewer is impressed with you. You've spotted the exponential complexity, and they might say to you, what are the problems you see when you do recursion like that with that really crappy function? Which actually looked kind of clever when we first did it, right? That lambda function, a one-liner. Woo! But there's other problems here. And this is an interesting thing when you get into efficiency. We can talk about it in terms of time, but we can also talk about it in terms of space. So how much space, resources of the computer is required? If we're not worried about time, how much space is required for this? I can go through the mental exercise of proving this to you, but basically what's happening is every time you call a recursive function, it is put onto the stack, and it's sat there for a while the rest of the chain resolves. Now in this case, we're doing an exponential spread here. Sometimes when you use recursion, you don't do that. You're just looping and looping and looping forever and using up the stack completely. That's a problem, because it can cause a stack overflow and shut your machine down. In this case, we're not doing that because the stack is smart enough to not put the same function on there twice. It uses pointers and whatnot. I won't get into it. But basically, we're using order n space. So if we're looking for fib 10, 10 is n. All we need is 10 spaces on the stack. That's what we're using. Why do we care? Because a lot of times in an interview, they'll ask you to balance big O time versus big O space. And you have to understand the difference. How much variable space do I need to be able to calculate something? All right, so let's fix this. This is where Fibonacci gets fun, because this is where we get to put on our engineer hats and try and figure out, well, how can we make something faster, use less space? This is the Fibonacci function that most people are probably used to seeing. What it's using here is a process called dynamic programming, and basically it just uses a caching mechanism. In this case, it's an array. I'm pre-filling the array, as you can see here, with the first two Fibonacci numbers, 1 and 1. Some people say it's 0, whatever. Let's just pretend it's 1 and 1. First two Fibonacci numbers are in there, and then we're looping over, looping 2 to n, and then we're using that array to calculate the further values. We're just using the previous values in the array to calculate the next Fibonacci numbers. That's exciting. It works. This is fast. So knowing what we know now about big O, how many loops do we see? 1. That's right. We have an array. That array is going to fill up according to what is being passed in. So we can say that we can have order n time, order n space. Your interviewer, that's all they're going to want to hear you be able to do, right? Can we get this down from n squared recursive hell into something more reasonable? And usually they'll be happy with this right here. If you were to write this code straight off the bat, they might ask you, why is this n time and n space? And then they might ask you, how can you get to order 1 space? Can you do this without an array? Does anybody in here know how to do this without an array? This is a fun part about the mental exercise of this. Can we do this without an array, and can we get this down to order 1 time without a loop? So think about those. I'll show you the one about space. There's a little process called tail recursion that you can use, and you can do recursion and using a variable as an accumulator. And this is something you see in functional languages a lot, because functional languages don't really have objects and state, so you have to pass along whatever you need. If you use MapReduce, this is kind of the way MapReduce works in a lot of languages underneath the covers. Tail recursion doesn't have an array. You're just setting a single value in a variable, and so you can get away with having order 1 space. So in this case, we have 1 loop, or the recursive loop, that still counts, and then we have order 1 space, which is a lot of fun. All right. I was in an interview just over a year ago. I interviewed at Google, did the Google chain. I don't know why. I think I like torture. And I went in there, and they asked me a question about tic-tac-toe, which is pretty fun. I was like, oh, I hate the interview questions. But at the same time, I tried to change my perspective on that, because I do like puzzles. And it's kind of fun to practice this stuff and see if we can geek out. And so they said, so I came up with a solution for tic-tac-toe. The idea was, here's a move from X or O. Did they win? That's all they wanted to know. And so I was able to write some code and used like a binary string, or I think it had nulls in it, I can't remember. Used some kind of string to show how the tic-tac-toe board might look to a computer. And I was able to go through it just fine. In the very end, they said, let's say we don't care about space at all. You can use all the resources of the machine you want. How can you get this down to order 1? Like, I need a loop, man. I can't get down to order 1. And they said, hack it. Just hack it. Think laterally. Hack it. And the answer is pretty funny. I couldn't believe it. I didn't get it, but they showed me. You just preload every single possible configuration of a tic-tac-toe table, put it into an array. If you're representing the tic-tac-toe tables as a bunch of strings, right? And then you just put it into an array, and then you compare the values. And so that would be the key. The winning value could be the key, and then you compare the value coming in. That's order 1. It's really hacky, but this is how you would do this with Fibonacci. Just pump out a billion Fibonacci numbers up to a billion, let's say. And then you want to know the position, the nth position, just go to the array and you've got order 1. I know. This is silly, this is ridiculous. It's a fun challenge. I had to know this stuff because I went through the interview loops at Microsoft. So one person did ask me how indexes work on Postgres. And I thought that was awesome that they asked me that. So to me, I look at these as a fun challenge. There's a movie called Glengarry Glen Ross, and one of the key quotes is always be closing. And so to me, always be interviewing is, I think, really good because it keeps your skills sharp. And when you really need to interview, man, you really need to interview, and you're going to have to get over yourself and learn all these things so you can go get a job. Again, it's also good for code reviews, but it's also good for spotting problems. And what we just went through was an exercise in spotting and improving problems. Let's talk about that a little bit more. We talked about exponential complexity. And if you're able to spot exponential complexity and work with it, it's kind of like playing with fire. You can be really, really successful at what you're doing, but if you try and do anything more, you could really get in trouble. Let me explain what I mean. I actually found myself in this position a long time ago. That's me. Wasn't I cute? Come on. So back in the early 2000s, I worked in an analytical company. I did a lot of database work, a lot of analytics. I learned a lot of fun statistics. And my boss said to me, I want a query that is kind of like an Amazon query. You know when you go to a product page and you see the related items, people have seen this, people have bought this, whatever. I want something like that. I was thinking, all right, I can do that. And this, by the way, are the most ridiculous items on Amazon. And I'm showing this to you for a reason. That is a book of 1 million random digits that someone is selling. There's also, customers who viewed this also viewed the yodeling pickle and the Kamaputra, and a really cool book about how to avoid huge ships, which can come in handy, especially if you work in .NET or JavaScript. Anyway, sorry, I just had a small dig there. The reason that this looks like this is because some magazine published an article, I think it was in Mashable, about the most ridiculous items on Amazon. So people kept clicking the links, and they'd go here, and so Amazon in the background built that association, so that's why you see this. And so that's what my boss wanted, except he didn't want just one item to show the rest of the items. He wanted to see all the associations. He wanted to know what are the top 2 items that are associated together, that people bought together. So if we look at this in terms of a graph, you might have, let's say we have just 7 items in our database. This is a nice graph. The edge weight of our graph between 2 nodes, 2 products, is the association. So this would tell us that SKU 1 and SKU 6 were bought together the most. For a marketer, that is gigantic information to know. It tells people the behavior of how they're using your site. Understanding behavior like this is an exponentially complex problem, but we can dabble in it a little bit because I didn't know any better at the time. I just said, sure, give me the database, let me at it. So I grabbed all the products, and I'm not going to step through all this code. I just want to show you that it was real, and I'm not making this all up, even though maybe I am. So I looped, I'm not making it up, I promise. I looped through all the products, and then I queried the orders table, got the order items, and saw what one product was bought with, and I got a set for the other products too. So putting on our big O hats, one more time for fun, how many of you can recognize the complexity of a routine like this as I just described it? Well, for me, I just try and do the simple thing. I have a loop right there, that's one, and then I have a nested loop down below it. I have to pull out the products, and then I have to loop over those products again, because it's entirely possible that one product, someone bought every other product with it, so we have an order n squared time complexity. And I went with this. I left it like this. Could I have improved it? Maybe. But I left it like that, and at this point, my boss might say to me, that is not cool. You're using an n squared, and that's a lot of data in our order system. Our order system is going to keep bringing in orders. This is a time complexity nightmare. And I said, ha-ha, that's okay, because I'm only running this once a night, and I'm loading up a results table. And that results table is going to be the thing that I look at. This results table is going to give me the associations that you're asking for. So I'm basically, as the solution was to tic-tac-toe, I'm basically preloading everything. This is the data, well, it's test data to show you. I can't actually show you the data I was working on, but we came up with some amazing relationships in the data. It surfaced this really neat behavior that the marketers really wanted to know. And they were able to go through and come up with specials and teases and mail things and whatnot, and my boss was super excited. I felt like a hero, and that was great, and so you know what's coming next. If we can do pairs, can we do triplets? Can we do 3 things? I was like, wow, association of 3 items? They're like, yeah, people buy more than 2 things. I want to see what, we want all the associations you can fit in there. And so we can kind of think about this now in terms of big O one more time. To do that, I would need to do another nested loop. Because once I had a pair, I'd have to go with that pair and see what else was bought with that pair and to come up with a triplet. So that puts me into exponential complexity territory. Why do we care about that? Because, well, I can say this now. Back then, I didn't have the words for it. But nowadays, I would just tell my boss, this is factorial complexity. We should not know. We can't, there's no way that we're going to finish this query. It might work today if we only have 10 orders. It might work just fine. But 5 years from now, when we have 1 million orders, we're going to be waiting all day and all night, and you're probably going to get mad at me. So hopefully your boss can see reason, because this is math. This isn't my opinion, man. This is just math. And so this is kind of the fun thing. This is what I'm going to end with today, is once you start seeing exponential complexity, you can't unsee it. I see it everywhere all the time, and it's kind of a plague. And my, hey, look at that. Are we done? I still have time, don't I? Geez, see, I thought I'd be boring you guys. I didn't think it'd be boring them, man. Come on, dude, shut up already. I was about to say it drives my friends crazy when I'm out with them. They're like, oh, and they just kind of turn around. No, but this is fun to me. Spotting problems that you're working on. So here, to kind of take this in the high level, imagine you're with some friends, right? And there's 5 of you, and you say, well, let's go do something fun. And you all look at each other. Okay, where do you want to go? I don't know, where do you want to go? Where do you want to go? I don't know, where do you want to go? And it gets kind of crazy, group inertia, right? When you try and tackle that problem, like what is the best place that, let's say all of us want to go to a pub right now. What is the best place for all of us to go? Well, there's a lot of concerns, right? What's it gonna take for all of us to get there? What are they serving? Blah, 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 blah. What you're trying to do when you try and figure out the best place is you're trying to optimize a combination of all kinds of variables. In this case, this is my daughter and her friends, and they were bored. We're in Santa Barbara on vacation. They're like, we're bored. I'm like, oh my God, it's Santa Barbara. Go to the beach, get out of here. So anyway, I went to the park with them because I'm not that mean, believe it or not. So what I had to consider at that moment, they're bored, and I was like, okay, I'm bored too. Let's all go hang out. What I had to consider is I wanted to have maximum fun for each kid. If we're all going to a pub, maximum fun for all of us, right? Minimum boredom, good conversation, but we're constrained, right? We're constrained by a few things, the time and the place, the weather, and whatnot. When you talk about this in terms of pure computational theory or complexity theory, this is what's called a combinatorial optimization. And this is something that I learned about, and my head went, boom, oh my God, I've been dealing with this a lot. You're just trying to optimize a whole bunch of variables, minimum, maximum, averages, whatever. You're trying to optimize that grouping of things to an optimal outcome. We do this every single day. In fact, there's another speaker at this conference. I heard he's okay as far as the speaker goes. Actually, Scott's my friend. I give him a hard time. I try and put his slides in my talk because he hates it. Scott has a thing about maximizing his keystrokes. Scott's kind of like a life coach. One of those life hacker people that loves to tell you how to live properly. And this is actually a good one. His whole point was there's a finite number of keystrokes left in your life. How can I make the best of those keystrokes in this message that I'm sending to somebody? And I think that's a pretty interesting way to live. But this isn't just him being a life coach. This guy's a total nerd, right? He went and figured it out, how many words he's going to type in the remainder of time that he has to type on this planet, right? He actually figured out that he has 168 million more words left in his fingers. And he went through the whole calculation. He wrote a whole blog post on this. Of course, nowadays, me being me, probably one of the most annoying people in the room, I look at this, and I instantly see this phrase right here. Is emailing this person back the best use of my remaining keystrokes? Oh, that's a combination of things right there. He's trying to optimize maximum word choice with minimum keystrokes. Oh, I'm excited now because this is a variation of a problem called knapsack. And it turns out there's a whole bunch of problems that are known to be NP complete and NP hard. And I'm not going to talk about all that. If you want to know more about that, please come up and talk to me. I'll talk your ear off. But it's kind of fun. There's problems like this that are variations of combinatorial optimization problems. This one's called knapsack. And the idea is that you have a knapsack that only holds a certain amount of weight. You want to pack in packages of varying weights. You want to have the most packages in there without going over the weight. It's a fun problem. It's also exponentially complex, which we know what that means now. Remembering that curve I told you to remember before. This is also exponentially complex. So if anybody ever asked you to solve a problem like this, like if Hanselman sat down and actually tried to calculate how he's going to do his email finger thing, I would just sit there and be the annoying one saying, you can't, man. Sorry, it's exponential complexity. You're not going to figure it out. There's 168 million words. Forget it. You're done. These signature problems that are worth your time to go look up, you've heard of some of them before probably. Traveling salesperson, click, bin packing, exact cover, knapsack you just saw. These are CARP's 21 NP complete problems, and they're really fun to go and just take a look at. There's a difference between NP hard and NP complete, and if you're interested in that, come up and talk to me later. But I do want to touch on this a little bit more, giving you some more practical examples of what combinatorial optimizations might look like. One of them is right here, right now, and it's standing in front of you. It's me on stage with this talk. With this talk, am trying to suck less every single year. I'm trying to get up here entertain you, have really fun, good slides, good content. In other words, I'm trying to optimize this talk by maximizing the visual impact of the slides, minimizing audience malaise, maximizing delivery within 60 minutes. So my annoying brain looks at that and says, well, that's bin packing, which is another combinatorial optimization, which means if I was to really try and deliver the optimal talk, I would be here until the end of the universe, because there's too many variables. That exponential complexity is not something to mess with when you have to think about scaling. It's fine if you only have a few items. It's not fine when you don't. Your project team, the software that you write every single day, you're probably part of a team, and you get together and you talk about what you're going to do next, what iteration you're working on. Maybe you're doing Agile. I don't know. I look at that in my annoying brain, and I say you're trying to optimize your project by iterating with minimal bugs, minimizing costs, maximizing client acceptance within a deadline. This is a variation of the problems we've seen. You could also say this is traveling salesperson. If you're not familiar with traveling salesperson, you basically have a bunch of cities, cost to go between each city, and the idea of the problem is that you're trying to go least cost to every single city, but only once. And to solve this, you can do it if you only have 4 or 5 cities. To solve this is exponentially hard, and you cannot get around that. Now, it's not impossible, as I keep saying. There are ways that you can solve these problems and be a hero, if you want. The one way is to apply a brute force algorithm. This is the true solution to all of these problems. And brute force algorithms, and by the way, I got this video off the internet. I thought it was really cool. It explains how brute force might work with traveling salesperson. You go through every single combination, and then you look at the overall cost of every single combination, and eventually you'll get down to least cost, and you'll get down to least path. That will work if you have 10 cities, maybe 15. You can be done in a night. If you have more than 20, it'll take you, I think they said 10 years, and then from there it goes on to decades and then millennia and onward, because this is exponential complexity. There are ways of solving this problem that don't involve brute force. Brute force is always going to take forever, but there are things called approximations and heuristics. Heuristics, just a rule of thumb. As it turns out, we know how to solve this problem as human beings. This is called nearest neighbor, and again, I clipped a little video off of this. Nearest neighbor is the way a human being might tackle this problem. Where am I right now? And what is the next cheapest city that I need to go to in this whole big traveling salesperson path? Well, I'll go there and hope for the best. And then you get there, and then you go, what's the next cheapest one from here? What's the next cheapest one from here, and so on. And then you end up with not really the optimal solution, but you end up close. You actually get, on average, within 75% of the optimal solution, which is pretty good, I think. It's not bad. But that's the one way to solve this. There's other ways using math to get around this, but the cool thing, if you use if you use nearest neighbor or a greedy algorithm, now you're down to order n, because you're only visiting one place once. So to bring this back to your project team, if you do Agile, this is where my annoying brain, like, people just like, shut up, man. If you do Agile, that is a greedy algorithm to solve the combinatorial optimization problem of your software project. I hate to say this, but the software project you're on is never going to succeed. Yes, no, it'll succeed. It's just exponentially complex to get the optimal solution, right? And all we can do is try and cope with that complexity using heuristics and algorithms like Agile. That's the way Agile addresses this problem. You go from point to point, and then at that point you say, well, okay, what's the next best place that we need to go given the variables that we know at this place and time? I know that the client wants this. We know that we've had these bugs. We know we want to address this. So you lay it all out, and you say, okay, well, we're going to go on this sprint and do this thing, go to this iteration. That is a greedy way of handling this. The cool thing about that is it's going to get you within 75% of the optimal project result. This isn't so bad. I mean, it's probably not the best thing. But the cool thing that you can do is you can just move the goalposts. You know, just change what your optimal outcome is, which is what most people do. They just adjust. And eventually, these two moving targets will make their way together, and boom, you're there. Contrast that with something like a waterfall approach, which is what a lot of big banks and institutions like to use. And if you think about this now, with your brand new complexity skills, these people are trying to tackle this combinatorial problem by thinking of everything up front, putting it into a massive document and saying, this is what we're doing. the chances of that succeeding are ridiculous, and you can prove that now mathematically. So if you want to go back and really maximize your chance of losing your job, tell your boss that if you're doing waterfall. Okay, that's I'll leave you with that. That's it for me. Thank you so much. I really appreciate your time coming, and hope some of this stuff was fun and exciting for you. Cheers. I guess I have some time for questions if you want to come up here. Or shout it out if you want to. If you want to. Okay, then get out of here.